So now we're going to consider gravity itself in Forces 3. Do you like the laser displays, by the way? I think they're brilliant. I think they're a real innovation. So we're going to start with Archimedes. Archimedes was the first one to understand anything about gravity, really. He understood that gravity works depending on what you're in. If you're in the air, you have one force of gravity down. In this case, you see something suspended in air weighs 20 newtons, and then when you put it in water, it weighs less. It weighs less. It has the same mass, but it weighs less because there's a force on it balancing it. The displacement of the liquid gives a force up. Now, the exact weight of liquid displaced, here it is down here as 8 newtons. That exact weight displaced is what we subtract from the weight as given by the Newton balance, by this type of scale. And so the upthrust is equal to the weight of the liquid displaced. And floating is basically the amount displaced by the body is equal to the weight of the boat. The weight of the thing which is floating is exactly equal to its weight displaced. Now, that is not Archimedes. It is a part of Archimedes that a floating body displaces its own weight. Actual Archimedes is saying that the upthrust is equal to the weight of the liquid displaced. That's Archimedes. And you can also use this to measure the density of a liquid, of course. When something's floating in it, the denser the liquid, the less you have to displace. If you have a very light liquid like oil, you have to displace a lot of it to cause something to float. If you have a very dense liquid, like whiskey, for instance, is slightly denser. It's one of the things they use. Or water, which is denser still, or mercury, in which cannonballs float. The smaller amount you have to displace because it's a denser liquid. And you use this to measure the density using a device called a hydrometer. Eric again. Hello, Eric. See, he's a star. He's everywhere. This is Eric the Camel explaining the difference between weight and mass again. Here he is in space, still being 900 kilograms, having the same mass. On Earth, he would be roughly 9,000 newtons, slightly more. Maybe he had a good meal since he was measured at 900 kilograms, and now he's 9,000 newtons. But in space, camels in space don't weigh anything. It's a well-known fact that camels in space have no weight because they're weightless. And we'll talk about that why in a little while. All falling bodies fall at the same rate. Galileo was the first person really to understand this. He was the first person to drop things and see that it didn't matter how big they were, they fell at the same speed. This is... no one ever gets this. I think this is hilarious. So, this is how we do the measurement of little g using a falling object. We take a ball bearing and we measure from the bottom of the ball bearing to the top of the trapdoor because that's the distance it's actually falling. We turn on the timer as we turn off the electromagnet. So the ball falls, hits the trapdoor and turns the time off again. The difference between the time at the total time taken can be used to calculate the acceleration of the ball as well as the height. We do it for different heights. We always take the shortest time. That's the most interesting thing about this experiment. Anything which causes an error usually makes the time longer. So the shortest time is the correct one. Another thing we can do is insert a little piece of paper just there, and that makes the ball release a little quicker. There's something called hysteresis which can build up in the ball bearing and means that the ball will not fall immediately that the thing is switched off. So we always take the shortest time for this experiment. The formula we used is just a corruption of the formula we were using, S equals ut plus a half a t squared. We have the t squared and the a is now the acceleration due to gravity we're looking for. The s is now the height. And the ut section there, well, u is 0. It falls from rest. So we use that. And I've also included the smallest value and the idea of the piece of paper. Okay, so this is another way of us looking at drag and friction. Just a little bit of a reminder, really. Nice to sort of throw it in at this point. This is the skydiver, and we're trying to work out his drag. He's still accelerating at this point. You might remember that he eventually reaches terminal velocity when his drag and his weight are the same, and he doesn't accelerate anymore. He travels down at constant velocity, which is called terminal velocity. So skydiving, now he's accelerating at this point at 2 meters per second squared. Now his actual weight is 784 because his mass is 80. 80 times acceleration due to gravity, 9.8, gives him a weight of 784 newtons. However, his acceleration is only 2 at the moment. So his force downwards is only 160. So it should be 784. It's actually 160, meaning that if we subtract the 2, we get 624 drag up. So that's 624 newtons. And going down, we've got his weight, 784 newtons. And the difference between them, the 160, is what's creating his actual acceleration. Now, what is a satellite? A satellite is something which is falling towards the Earth at the same angle as the Earth is falling away from it. If you fire a cannonball and it lands a long way away, it's travelled in an arc. It's travelled in, essentially, a circular type path. Now, if you fire it parallel to the Earth with exactly the right speed, it travels around the Earth constantly at that speed. And essentially, when we put something into orbit, we're firing it so that it's falling towards the Earth and the Earth is falling away. Now, because it's falling towards the Earth, as the gentleman in the lift in the previous section, because it's falling towards the Earth, it has no weight. It is weightless. And everything inside that cannonball, or satellite, or space station, will also be weightless. People who are orbiting the Earth are not weightless because they are so far from the Earth. They're actually not that high up. The space station's only a few hundred kilometers up. Why are they weightless? They're weightless because they are constantly falling towards the Earth as the Earth falls away from them. It's like you jumping off a diving board and never hitting the swimming pool. That sensation of weightlessness as you fall is the same all the way down. Now, Newton, mathematics, came up with this inverse square law. This inverse square law is just saying that, first of all, gravity is always positive, that it's related to the product of the masses involved, so our mass times the mass of the planet we're standing on, and is inversely proportional to the square of the distance between them. Now, it turns out nature is full of these inverse square laws. It's got to do more with anything else than the surface area of a sphere, which, if you think about it, is a square of the radius. And here we have a square here. But it's inversely proportional here, i.e. it gets smaller in the same rate. So if you're twice the distance away, you've a quarter of the force. That's the essential thing to remember. If you're 3 times the distance away, you've a ninth of the force. It's a square of the distance that you've reduced by. And that's called an inverse square law. And with all inverse square laws, and with all laws generally, we can turn proportionality into an equation simply by adding a constant. This is the constant, the universal gravitational constant. That turns our proportionality into an equation. As it happens, because gravity is universal throughout the universe, it has a universal rate. When we send things out into space, we often write on them this number to show how our number system works, because the universal gravitational constant will be the same everywhere in the universe. And if anybody ever finds it, they'll be able to look at this number and say, oh, well, if that's the way they write our number down, we know that we write it, it's easy to go from one to the other. And they'll be able to work out our entire number scheme from this simple representation, the idea of the universal gravitational constant. Hooke's law, force is proportional to extension. As long as you don't exceed the elastic limit, simply means that the more force you put on, the longer it gets. Not how long it is, but how much longer it gets. That's the extension. So the force means more extension. And proportionality. double the force, double the weight, double the extension. Not the length, the extension, how much longer it's got. And there are some examples of us starting with a force of 0, adding 6 newtons and making it 3 centimetres longer, so that if we add 12 newtons, twice the amount of force, then we'd get twice the extension, 6 centimetres longer. And if we had 4 times the original force, we'd have 4 times the extension, 12 centimetres. And that's all this slide's meant to represent. It's a proportionality. The interesting thing was that Hooke was probably the first person to write down a mathematical law from an experiment. A very important step in science, which is, frankly underrated because Newton hated him so much for some strange reason no one's ever been able to explain. But he really did dislike him. And Hooke ended up without any portrait. We don't even know what Hooke looked like because all of his portraits were destroyed by Newton. Strange thing to do. Here's, well, you can just read it. Freeze frame. This is the Toy Story version of physics. I like it better than me, actually. I wish I could explain things as well as this. Basically, as you can see, Bo Peep doesn't weigh as much as Buzz Lightyear, and Rex weighs so much that he exceeds the elastic limit. Really, the dog's not happy, is he? Not happy at all. Mathematically speaking, it's much easier. The weight, which is the force in this equation, we write it as force is a constant times extension, the constant being called the spring constant, if we're using a spring, and the extension being the difference in length. But actually that force is weight 90% of the time. So we're often given the figures in terms of kilograms, and we have to multiply it by a little g to get the weight, which is the force in the equation. So force and weight are the same thing. Mass is not. Mass is a different quantity, and we have to multiply the mass by the acceleration to get our weight. On Earth, that acceleration is 9.8. And if we know the extension and we know the weight, we can work out the spring constant, which we can then use in the second half. For a new force, we can work out what the extension would be. And that's essentially what's happened there. We've worked out K, and then we've used K in the second one to work out the extension. Okay, this is so sad. This is one of my favourite animations. This little gift, this gentleman walks up the steps, and when he gets to the top, his total work done is the distance he's raised himself times his weight, which gives us potential energy as well. The work done is the energy converted. And there he is, sadly standing at the bottom of the stairs. But you can go to my website, on the WordPress site, which is included in the notes, and you can see him walk up the stairs, and you can go through all the slides, not just the ones I'm talking about here. And maybe now I've talked over them for maybe the 7th or 8th time to you, some of them might make some sense. This one is meant to illustrate that the work done in climbing the staircase is the same as the energy converted, so that when he gets to the top, his potential energy is the same as the work done. We can also use this with a pendulum. As the pendulum is at the top of its rotation, its potential energy is maximum. It stops for a second in order to change direction. As it stops, it has no kinetic energy. As it reaches the bottom, that's the lowest it is able to go. The string will not allow it to go any further down. So it no longer has potential energy. It now only has kinetic energy. So in a perfect pendulum, the potential energy at the top is all converted into kinetic energy at the bottom, and we can use this in calculations. And I'm hoping you will use it quite soon. There it is, potential energy equals kinetic. This is the formula of potential, logbook. This is the potential for kinetic energy, logbook. Don't need to remember them. There we are. So the potential energy at the top, it's 10 centimetres up. We put the two equal to each other. Of course, mass isn't important. The mass of the pendulum bob doesn't have to be considered because they cancel. We end up with v squared equals 2gh. We put in the g, 9.8, the height, which is 10 centimetres, is 0.1 of a metre. Multiply everything together, and we find, once we've square rooted, that the velocity of the pendulum bob as it passes through the central section is 1.4 metres per second. That's what we've calculated. Of course, up here, the velocity is 0. As it changes from going up to going down, it must pass through 0, like passing through go in a Monopoly board. Finally, power, which is the rate at work is done. So if you do some work, and work is done force times distance equals work. If we multiply the force, again the weight, by the distance it's been lifted, we get the amount of work done. To find the power, we divide that work done by time. Again, this is all in the logbook. These are all formulas from the logbook. Now, this type of question doesn't come up very much, so I'm not going to stress it hugely, but this is quite an important section. When we come on to heat, you'll need to understand that power is work done or energy converted or energy used divided by time. It's a rate, and anything which is a rate is divided by time. Okay, 2 questions for you. This one on the pendulum. I've pretty much gone over that just recently, so I'm not going to worry about it. Draw a labeled diagram on the forces acting on the mass when it's at point B. Well, the actual only force acting on it besides the tension in the string, of course, is the weight down. So you've got weight and tension. Then you've got a downhill skier, which kind of ties together some of the ideas from the last 2 slideshows. So 2 half questions these are from question 12s over the years, which is where you'd probably use this section more than anything else. So there we have it. We're well into forces now.